Good afternoon, everyone. In the today's class, we would like to continue regarding the milling machine working process and continue to the yesterday's class that we have been discussed different classifications regarding the milling machines, different types of milling machines, and its working agitations. In the today's class, we would like to come across the different types of work holding devices utilized in the milling machines. And furtherly, certain advantages and limitations that are being utilized or that are existing regarding the milling machines. Coming to the point of this work holding devices, Vises, which are playing a crucial role for holding the objects at a convenience level of strategy. And the next thing is the parallel strips. Nothing but in the case of this milling machine, it provides a solid seat and raise the work above the considerations. Nothing but the level of maintaining the surface finishings. So in the pictorial representations, we used to grasp the two devices, that is the vise, which is utilized for holding the object tightly upon screwing this by the manual process, holder process, screw holder. Upon tightening, the lever will be getting in converging situation that holds the object tightly, and certain operations, nothing but the milling operations towards its base or top level or side level will be getting considered. And upon pre-releasing or direction changing of the object, we use it to again unlocking the holder by counterclockwise rotations and next changing the position or direction of the work parts and machining over the work part for the convenient dimensions obtaining. Second thing, that is the clamps, different types of clamps. Here we are having different dimensional oriented clamps. First thing, it is strap type of clamp, gooseneck, which is the adjustable clamps utilized for holding the work parts, and U-type or U-shaped type of clamp for holding the objects up to a non-extinguishable strategy levels. Moreover, these clamps are used for having the secure work, particularly in the case of the work parts doesn't have a particular shapes, confined this particular shapes. Basically, it's a very much large and need to have a fit condition into the vises. In the typical cases, these clamps are utilized for commencing the work strategy such as cutting process, fitting process, holding up the objects very much tightly in the case of heavy cutting processes, where we need the heavy cutting processes. Coming to the process of this cutting speed, coming to the cutting parameters, we are having three basic phenomena. First one is the speed, second one is the feed, third one is the depth of cut. Speed, feed, and depth of cut. Considering this cutting speed, is the relative speed between the cutting tool and the work part. and it will be asked or calculated with respect to the meters per minute. So the material that has been removed upon the friction developed between this working tool, or simply we will be calling as a cutter, elevating the material in the form of a mini chips per minute, how many meters that over the surface of the work part the cutter is being measured. Nominally, this cutter is having with respect to a small diameters that revolves at a fixed axis, which is fixed within the arbors, and work part used to slide over that particular cutter for getting the MRR activity, material removal rate. So how we will be calculating this speeds? In the nowadays, we are having this digital tachometers for identifying the speeds or that are maintaining within the arbor or machinery unit without any contact. So certain radiographic technology will be utilizing upon passing the UV radiations. Directly transreceiver, it transmits the UV rays and receives the signal back to its source position again, and the 7 segmental display will highlight the speed and number directly in the display. Particularly, this cutting speed is a major factor for commencing of the work within less time, or within, it might be taking a long time period. That too, the timing zones will be depending upon the type of materials that we are utilizing in the case of work part, and related to the work part, selecting the particular tool materials which are capable of working on the work parts. Coming to this factor, the cutting speed, it's directly depends upon the cutter material, workpiece material, surface finishing, and depth of cut. See, having the 4 major parameters. Cutting speed depends upon the cutter material, workpiece material, surface finishing, and depth of cut. Coming to the cutting speeds for standard materials, upon experimentational process, the standard values of this cutting speeds are here mentioned in the table or column. Aluminium is one of the material, is a non-ferrous content of material, will be having high strength to weight ratio capacity, less weight, and have the capability of withstanding the maximum load implications over the material, which in turn plays a maximum major role in the manufacturing of aviation parts and even in the different kinds of automobile parts. Next, moving on to the brass material. But in the case of this aluminum, the cutting speed can be commenced by the tool that the material of aluminum accepts 100 meters per minute. Coming to the brass material, 45 meters per minute, the material MRR process will be getting conditioned. In the case of this cast iron, which is having an major part of this ferrous material. In order to machine over this cast iron object, 20 meters per minute will be getting machined. Coming to the mild steel, 25 meters per minute. In the case of this high carbon steels, 15 meters per minute can be machined. So that is related to the work part material and suitable cutting material that will be getting selected, and upon both the combination the work will be getting progressed. See, for identifying this speed, nothing but number of rotations per minute, nominally n is equal to cs by pi into d. We all know that cs is nothing but the cutting speed in meters per minute, that is associated with respect to the spindle speed, which in which the cutter is getting engaged with it. And the standard value of this pi is equal to 3.142. And next thing it is the diameter of the cutter. It is a standard value that will be depending upon the type of materials. So in order to identify this number of revolutions per minute has been commenced, that n is equal to cs by pi into d is the formula for calculating the number of revolutions per minute. Let's have a simple example. Calculate the speed that is required to cut a mild steel workpiece, that too within a 75 cutter in diameter. So here we are having diameter d value is 75 pi value that is 3.14, and from the initial table the standard values need to be kept in mind, that is depending upon the materials. For mild steel that's 20, cast iron 25, as we have been just seen, cast iron 20, mild steel 25, high carbon steel 15, brass 45, aluminum is 100. Hence in the question the material that has been given, that is mild steel. According to the tabular column, mild steel is having 25 meters per minute of capability. So that you should remember with your mind, or else the tabular column you should keep in your mind, or else you have to refer with respect to the data table, data tables that will be provided to you in the examination times. And hence from the table we are having a standard value that depending upon the mild steel material, it is clear that the value or cutting speed per meters in the case of this mild steel is 25 meters per minute, and the diameter has been given, that is 75 cutter diameter. So 75 by 1000, that is 0.075, because 75 it has been given. So conversion of the values into meters, so 0.075, because the values are entirely existing in meters. That's why converting to meters. Next, we are having the formula n is equal to cs by pi into d. So d value is having here, and cutter speed we are having here. Next, substituting these values, we are getting 106 revolutions per minute. So these are the simple problems we'll be facing in the case of examination point of view, that too for 2 marks or 3 marks range of problems. Next thing, next cutting parameter, it is a milling feed or feed rate. So speed calculations we had a detailed look, and feed calculations, and next towards the depth of cut, and this is also the cutting feed rates depending upon different types of materials. Nominally the basic definition of this feed rate is nothing but the rate at which the work moves into the revolving cutter and is expressed as millimeters that the material has been removed from the parental material upon working process. So feed rating in the sense here by the tool teeth, the feeding will be given. That means penetration, we can say penetration of this cutter to the work part over the work part. Why? Because for the commencement of having the consignment of this cutter indeed to operate over the work part by removing the material. So this feed rate is particularly depending on some parameters. The first one is the tool pitch, that is nothing but how many of the teeth does that particular cutter will be having. Rigidity of the workpiece, nothing but how securely as the workpiece that is held. The quality of finishing that is required after the committing of this working process. The type of, based on the type of workpiece material, nothing but aluminum, brass, cast iron as specified in the tabular column clearly. Next, the width and depth of cuts based on the depth and depth of cuts. For the standard materials, which plays major phenomena in the real-time work basis, that feed per tooth in millimeters. Coming to the material and slab milling and side and face milling operations, slitting saw operations, shell and milling process, slot drill and milling process. So these are the operational processes in the case of milling machines. That the aluminum, in the case of this aluminum, particularly that the slab mill is 0.30, having the feed nothing but removal rate of the material is 0.30 in the for the aluminum in the case of slab mill operation. In the case of side and face milling operation for the same material, that is aluminum, they are having 0.25 in mm. Slitting saw process in the case of the same material aluminum 0.01. Shell and mill process for aluminum material 0.40. Slot drill and mill, that is 0.06 mm. Particularly in the case of brass 0.20, in the case of slab mill operation. Side and face operations 0.20 for brass material. Slitting saw for brass material, that is 0.008 millimeters. Shell and mill process, that is 0.30 mm. Slot drill and mill 0.05. Cast iron slab mill operation 0.20 mm. 0.20 in the case of side and face mill. Slitting 0.01. Shell and mill 0.30. Slot drill and mill 0.05. Simultaneously for mild steel material, it is high strength material and high weight containing of material also. In this, for the slab mill operation 0.10 and side and face milling 0.10, slitting saw 0.05, shell and mill 0.20, slot drill and mill 0.05. High carbon steel materials for the slab mill operation 0.08, side and face 0.08, slitting saw process, that is 0.0025, shell and mill 0.15, slot drill and mill, that is 0.03. So these are the feed for each and every tooth in millimeters has been calculated during the working process for different kinds of materials. That too for different processes that are being worked out in the case of this operations. How this calculations of feed rate is being considered. Feed, that is limits per minute, that's equal to n number of number of teeth in a milling cutter into the product of f. So f is nothing but ftp per revolution per minute, nothing but fpt, feed per tooth, into revolutions per minute, that is revolutions per minute that has been commenced by the milling cutter. So here we need to calculate the feed as some product of number of teeth in a milling cutter to the feed per tooth for a particular cutter and a metal, and the product of revolutions per minute of the milling cutter. Let's have a simple example here. A 75 diameter side and face mill cutter having 8 teeth that is used to cut the mild steel material using spindle speed 106 revolutions per minute. Find the feed rate. So here in the question, it is very much clear for us that given the speed, so speed is nothing but the revolutions per minute, there is nothing but 106 spindle speed, 106 revolutions per minute has been given. Next one, feed per tooth. So it need to be converted from the basic table or column. So here, what is the type of material that will be varying with respect to the type of materials, and n number of teeth. So how many number of teeth they are having? Here we are having diameter also. Anyway, diameter doesn't matter for us. In the formulation, we need to have only the how many number of teeth that we are having. So 8 teeth. So 75 diameter side and face mill cutter having 8 teeth. So n is equal to 8, and revolutions per minute, nothing but the speed, that is 106 revolutions per minute, and here we require only the fpt, that is feed per tooth. So what is the material utilized for the cutter? That is particularly in a process, going to the process, face side and face miller, and the material it is cutting mild steel. Going to the table, moving on to the mild steel, and side and face cutter, that is 0.10. So that is the answer, that is 0.1. So fpt is 0.1. Substituting these three values, so we are having the feed rate calculations for per minute is speed into the product of feed per tooth into the product of number of teeth and a milling cutter. As the feed rate is equal to 8 into 0.1 into 106, that's 84 per minute. So 84 of feed will be getting acetated for the required parameters supplied. So cutting oils, why these cutting oils will be placed up here? We are having basic advantage, nothing but here the name itself, it is clearly specifying that cutting or coolant oils. Coolant is nothing but limiting of the temperature. So why the temperature will be taking place? Yet the coefficient of friction that is being developed between this work part and the tool, or coefficient of friction that is being developed between the work part and the tool. Normally upon machining process, tool will be getting engagement with respect to the work part. The coefficient of friction develops. Because of that friction, automatically the temperature that produces, in order to limit the temperature, this coolants will be utilized. Because if at all we have not limits that particular temperature, more amount of temperature leads to destruction of mechanical properties of the material as well as the tool. So at that particular situations, either tool will be getting destructed or else the work part will be getting destructed. So we are having the dual drawbacks. So it dissipates heat to the atmosphere upon utilization of these coolants. Particularly, it limits the temperature up to a normal range that gives the long life to the cutting edge of the tool. Normally, the oil that is also lubricates the cutter face and flushes away the chips. That is what for material removal also it helps a lot. Coming to the conventional strategy, we are having two different types of milling processes, that is up milling and down milling. Up milling is nothing but cutting of the uh, cutter is a constant and workpiece will be getting moved for a same direction of the tool position also. Particularly, we can say that work part will be in opposite strategy. By this, the chip formation will be from and its thickness will be starting at the point of cutting cutter initially and to the end of the work part cutter. It starts with minimum and increases to a maximum range. Similarly, in the case of this down milling cutting, it is quite opposite. Initially, it will be having a high chip dimension at the cutter mating point, and at the leaving condition, it will be minimum. That is quite opposite. So, this is the gear cutting machine. Particularly, it's the process for creating the gears, which we'll be utilizing in automobiles alignments. This utilizes for hobbing, broaching, milling, and for grinding process. Coming to the gear cutting method, it is processed by a single point form tool by a shear speed shaping process. Gear milling is configured using an formed end milling, gear broaching, and template methods. Coming to the advantages and limitations of this milling machine, coming to the point of advantages, the metal is removed at a faster rate as the cutter has multiple cutting edges and rotates at higher speeds. Normally, it is possible to perform machining by mounting more than one cutter at a time. Nothing but upon mounting, the cutting process will be getting done, and unitary status it is maintaining simultaneously, and maintaining of an accuracy of 0.02 mm. And particularly, it is useful for various cutters and precise tools that use it to be machined, that can be machined. Nominally, special attachments are mounted on a machine in order to perform the operations which are performed in other machine tools also. Coming to the point of this quality, it's enhanced with the presence of this machine. High qualitative products will be getting achieved with good dimensional finishings. Coming to the limitations, in the economical point of view, it is very much huge in cost. Even the mill cutters also is very much cost, and entire this investment relates to an huge in economy. Obviously, the product cost also will be increasing. When compared to the shaper or drilling machine in the production ratio. These are the some of the limitations for the milling machine. Thank you. We'll be meeting in the next class.